Okay, hello there. In this video, we're going to be exploring how the mean value in a distribution can mislead you. So to cover this, I'm going to be going over 3 different examples. The first one is going to be about a heart rate monitor that enters cadence lock. So this happens quite often, and especially if you have an optical heart rate monitor, basically it looks at your running cadence, how fast your legs are moving, as your heart rate, which can mislead you. We're also going to be looking at hospital waiting times and walking into a room with ultra wealthy people and how that can all mislead you. So, okay, first things first, we're looking here. I'm going to be doing these examples in Python, so all the code is going to be displayed. I already typed it out. There's going to be plots as well. Basically, the channel is just me trying to explain these concepts for one, and also practice coding with them. And yeah, the goal is to improve, basically to explain these concepts, and also to, if anyone watches, to teach them something about this. So this channel is going to be focused on statistics, data science, these kinds of topics. I'm starting from kind of the very beginning. Anyways, okay. So here we have example 1, heart rate monitor cadence lock. We have a running duration, you're jogging around for like half an hour, and for about 10 minutes, the heart rate monitor is looking at your cadence, which is typically higher than your heart rate. And we're saying we have a sensor frequency of 5, so basically it's looking at your heart rate 5 times per second, so 5 hertz. Here we define the number of sensor readings. So this is the number of correct ones, incorrect. And basically, type it all in. What do you get? You get a mean value of 145 beats per minute, but a median of 136 and a mode of 138. So the value that appears the most often is 138 beats per minute. The median, or kind of slice this data in half and look at that value, well, the median is 136 beats per minute, and the mean is 145. Now, if we plot this out, you will see exactly what happened. So this is the cadence lock, right? The data is looking at your number of steps per minute. It sees, okay, well, this heart rate is pretty high. You're around 168 up to like 175. And this is what your actual heart rate is. This is the accurate part, inaccurate part. And because of this discrepancy, you have a mean that is significantly higher than the actual middle, right? The mean, median, and mode are all measures of central tendency, where your data tends to cluster up. And if your data isn't clustering, right, like this, if there are significant outliers, then the mean is pushed away from the reality. It still presents what the actual information it's still a valuable measure, but it looks at the total instead, the actual total values, instead of the positional values. So keep in mind, in this case the median is more accurate than the mean for the reality of what happened. Now, okay, our example number 2 here is going to be a room of ultra wealthy people. Imagine this, you're going to a party or something, and there's about 250 people there. Most of them have a yearly income of about 50,000 with a standard deviation of roughly 10,000. Now you have ultra wealthy people hiding there. You got Bill Gates and I don't know, maybe Warren Buffett, and I just put a random value here, 120 million per year as salary and 99 million for the other person, held in stocks. So these are these values. And these people are obviously many times richer than the rest. So what happens to the actual mean income, the average income? Well, we see here, it becomes 919,000. And remember, the normal income is 50,000. So the median ends up being 50,759, much closer. And the mode is, well, I don't know how I got to that, but the value that appears most frequently, 22,000, doesn't really apply in this case, even though it's still more accurate than the mean. Okay, so here we plot this out, and we look at the incomes. So here we have the distribution. It's a fairly normal distribution when we have the billionaires removed, and we see that the median lands pretty much straight in the middle, right? Normally distributed, there's not a whole lot of skewness or movement away from the center, right? So we see here, okay, cool. But now if you look at the incomes with the billionaires, well, you have everybody over here, and then billionaire number 1 over here, and billionaire 2 over here. And you look at this, okay, well the mean is 919,000. Because these values are so high, the mean still looks like a very low value, and it is. But if we were to zoom in on this, as we've seen here, I mean the mean isn't even shown because it's about 10 times higher than like the maximum value you see here. So keep that in mind. I hope you're starting to see an image here. Now, example 3, hospital stay durations. So let's say you're at a hospital, you have 600 patients there, and we're giving, again, for the number generation, rough values. Long-term stay has a ratio of about 8 out of 100 people there staying long-term. So we calculate the values. If you know Python code, you can kind of decipher this and see how the data is generated. But anyways, so we do this, we generate the data, and we see that the mean value is 8.35 days. Whereas here, in our short-term durations, we're creating data between 2 and 5 days, right? That's like the typical patient, essentially. Whereas for long-term, well, we have between 60 and 80 days. And this is being created as a random integer, evenly distributed. So, equal between all of them. And there's obviously a lot less of these people, but nonetheless, because they're in this distribution, it creates a different mean. And we see here, mean, median. 3.0, the median, once again, falls kind of in the middle of our short-term duration, but the mean, way above. And the mode is also very accurate here. And then we plot this out, and same thing as with the billionaire scenario. We see a lot of people at the start, right? These are the majority of patients who are staying there for a short time, but you have a significant amount, still enough to skew that mean closer towards this. So because they're staying here for so long, the actual mean, once again, does not become a proper measure of central tendency. So we see the cycle repeated again and again and again. And in cases like this, what you would do, well, in this case, you would basically create 2 categories, right? You have 2 different distributions, and you would separate them out. So this could be like category A, category B, short-term, long-term. And that way, you don't have 2 separate distributions in one. So, continuing on, as we've seen above, the mean is clearly not the best measure for all cases, of course. And now, if we do this data again, we can look at an actual bimodal distribution. In this case, we're basically modeling a commute. So for a car, we would say that, the average commute's about half an hour, standard deviation of 7 minutes. So it varies quite a lot. Some days traffic is much more dense than other days. And then we have the average commute for a train, and the train is longer with less standard deviation. Now these are 2 separate distributions in one. And when we actually look at the mean and the median, oh no, what? And P is not defined. Oh, I guess I gotta restart everything here. Okay, there we go. NumPy is now imported. When we look at the mean and the median, they're both inaccurate. In this case, because we have a similar, actually exact same size for both of these, so we have 10,000 examples for the train commute and 10,000 examples for the car commute. In this case, the median and the mean are fairly similar. The mode makes absolutely no sense, but I guess it is I don't know how that happened, but anyways, we look at this. This is what the distribution looks like. So as you'd expect, you see the car commute is more spread out because it has a higher standard deviation. It's normally distributed. And then you have the train distribution, train commute, more tightly clumped together, more centered, but its mean would be about over here. Its median would also be about over here. And the car mean would be about over here. But when you combine the two, what happens? The mean and the median simply don't explain, right? It's become a scenario where actually both are very similar in not explaining what's happening. They tell you the average between both, but not for either or. So this is a case where the median and the mean are simply not proper. And in this case, you look at the mode if it worked. That the way that I have that function defined is not all that great for the mode, but basically you would have two modes, right? That's what it's called, bimodal. You see that the value for the central tendency would have multiple values. So you have one over here and one over here, and that would show you what's happening much better. Okay, so final one, we're going to look at an exponential distribution. This is one that starts off with a high frequency, but over time, or over whatever measure you're looking at, decreases exponentially. So here we're looking at like a server example. So imagine you have a server, right? You're getting a web page and you need a response. So we're saying the average server response time is 10 milliseconds. And there's about 25,000 requests per day. So here we can use the stats module from SciPy to generate our exponential data. And then here we have all the stats. We can print that out. So here we'll see the mean ends up being actually exact and perfect, which makes sense because we defined it here after all. And the median does not actually describe the data that well. The mode does absolutely nothing. And as we go over here and plot it out, you'll see what happens. So in this case, the mean is actually very good. The median too, but there is no real central tendency, right? There's in a lot of these distributions, right? You might have a uniform distribution where you're rolling dice, for example. It's the expected value. So the mean and the expected value are kind of synonymous for the most part, but it's basically if you were to run this many times, right? If you had like infinite samples, then it would converge to this value, which you might not even be able to get. Well, in this case, you are absolutely able to get, but for like rolling dice, it might be 3.5, right? You roll the dice, you have a value of 1, you roll it again, value 2, value 6. You do it infinite times, you're going to have 1/6 of the time, you're going to have 1, and then 2, and then 3, and you add them all up, divide them by 6, and you find 3.5 as your value. So anyways, the relative frequency here, you see the mode does make perfect sense. The value you see the most is 0, or right around 0. And then, which in this case wouldn't even make any sense, so forget that. But, boom, you see this. It increases up until very, very large values, exponentially lower. So overall, what you learn here is that, well, for one, the mean is very interesting, and kind of continuing on from the last video, is that the mean doesn't tell you the whole story in a lot of cases. It's good to have, and I'm going to go over variance and standard distribution in future videos. But the mean, right, adding all the values up and dividing them by the number of samples or values that you have, it won't always work. So if you look at data where there's a strong disparity, or you suspect that there are significant outliers, then you might want to look at the median. Or if it's two distributions in one, as we see in here with the car and train commute, you might want to use mode instead, right? You'll find the mode of one n of 2, assuming that they appear roughly the same amount of times, and use that as a rough measure. So depending on your distribution, you're going to use different measures of central tendency. So yeah, overall, thank you for listening, and see you tomorrow.